Okay. Okay, sir. Yes, sir. Okay, let's start our today's class. And my dear students, today I'm going to talk about another important topic in econometrics. As an econometrician or statistician, right? Or as a data modeler or data scientist, right? When you are gonna analyze your data, it can be econometric, it can be medical data. You might face another problem in your data. What is the name of the problem? The problem is heteroskedasticity. So today we are going to talk about this important topic, heteroskedasticity. So let me share my slide. So I think you have already some idea about the previous problem, multicollinearity, right? But today we are going to talk about another problem. It's called heteroskedasticity. So you can see the figure, right? The one figure illustrates the problem homoskedasticity, and the another figure shows you another problem is heteroskedasticity. Which one is good? Which one is bad? Could you please tell me?
Homoskedasticity is good, but heteroskedasticity is bad for our model fitting.
Okay. Okay, this is a very good knowledge you have already. At least you can identify which one is good, which one is bad, right? Let's go. I think after the class, you will have a good knowledge about both topics. Anyway, let's start. So one of the most important assumptions of the classical linear regression model is that the variance of the disturbance term UI is constant. Okay, UI means the error constant. That means if you can take the expectation of the error terms, like, then it will be the variance sigma square. So this is the assumption of homoskedasticity. So there are two words are here. One is homo, it means equal, and another one is the spread. Spread means the skedasticity. It calls the equal variance, right? So homoskedasticity means the equal variance. So it's a normal common sense, like you have an error term, right? Not only one error term, suppose you have a series of error terms that has been occurred in your data set. If the error term is constant, this is good. Or if the error term is not constant, this is good. What do you think? Answer me.
If constant, then it is good.
If it is constant, so error is a bad thing, definitely. But if you can find the constant pattern of the error term, that is good. Why? You can easily trace, or you can easily identify, or you can easily fix the error term because the pattern of the error term is constant. You got my point or not?
Yes, sir.
That means the pattern, if the pattern is, if you can identify the pattern easily, right? For the error pattern, then you can fix the error easily, right? That is the constant thing. That means it's changing, but the changing is equal pattern, right? So that is a good thing maybe in the classical linear regression. So one of the most important assumptions of the classical linear regression model is that the variance of the disturbance term is constant, right? That means this assumption is called the homoskedasticity. That means equal variance, right? Homo means equal, and skedasticity means the spread, right? So the homoskedasticity means the equal variance of the disturbance term or the error term in a regression model. So this is the one of the most important assumption I think you already know from the classical linear regression model assumption. What happens if this assumption violate, right? Then the problem begins, and this problem is called the heteroskedasticity. But in some situation, when this assumption does not fulfill, that means the as a variance of the disturbance term is not constant, then this problem occurs. The problem of heteroskedasticity occurs. So we can define the heteroskedasticity like this. The non-constant variance of the disturbance term is known as heteroskedasticity. You understand? The non-constant variance of the disturbance term is known as heteroskedasticity. So if I ask you, the constant variance of the disturbance term is called what?
Homoskedasticity.
Very good. So the constant variance of the disturbance term is called homoskedasticity. So naturally the non-constant variance of the disturbance terms might be called heteroskedasticity, and this is really a problem. This is really a problem because a data modeler, a good data modeler used to model a good fitting model, right? So that he or she can fit the model very well. And ultimately our prediction, we are looking for a good prediction of our data, okay? So if your data suffers from this kind of problem, the problem like heteroskedasticity, then your prediction or your estimation of the model is not gonna be good, right? So this is a problem in our, mostly happens in econometric data, economic data or medical data also maybe, but mostly in economic data you'll find heteroskedasticity problem. But in multicollinearity, it normally occurs in medical data. Anyway, so when you will face this problem, when you are going to analyze something as far as data is concerned, like you have to remove this problem normally, right? Anyway, we'll try to learn how to remove this data. But before that, we need to know how it occurs, right? And what problems really you can find in your data if this kind of problem presence is present in your data set. Let's see, let's move. So what is heteroskedasticity? Again, I have to repeat, heteroskedasticity often occurs when there is a large difference among the size of the observations, right? Normally, when the observations are differ from each other, and if the difference is really a large difference, then you might suspect that the non-consistent variance might occur there, right? So a large difference among the size of the observations is the basic visualization is like that a problem might occur there, right? A classic, so what is the classic example or normal example for heteroskedasticity? Like when the large difference among the size of the observation you might expect when, I want to give you a practical example. Suppose income versus expenditure. So what is the normal procedure like? Suppose you have a lot of incomes, so normally your expenditure is gonna be increase also, right? So as once income increases, the variability of food consumption will also increase. So this example, you can think, this example is a very good example for large difference among the size of the observations, right? Like you have a lot of incomes, you have a lot of expenditure, right? And sometimes maybe your income is constant, like your income is not good enough, but still, because food consumption is a habit, right? So when you are habituated with something, so it's difficult to come back from that habit. So anyway, these examples clarify, or for this example, you might see a large difference among the size of the observations, right? Then when heteroskedasticity occurs when there is a large difference among the size of the observations, right? So what is the cause of heteroskedasticity? Why heteroskedasticity occurs normally in the data sets? So I can tell you heteroskedasticity occurred due to the presence of the outlier in the data. So what is outlier? You already know what is outlier. What is outlier? Could you please tell me, anybody, what is outlier?
The extreme value. Extreme value,
The really smaller or greater value.
Okay, like
or extreme value, sir.
Exactly, this is okay. Like the value, right, which is totally different from the rest of the value, right? The difference means it can be very big, it can be very small. So I have to say that the totally different value from the rest of the value, or the extreme value, is called the outlier. So normally when you will find a lot of outliers in your data, okay, then heteroskedasticity might be present there. So this is the suspect, like the primary suspect, okay? outlier in heteroskedasticity means that the observations that are outlier, it might either small or large with respect to the other observations are present in the sample of your data. Heteroskedasticity is also caused due to the omission of variables from the model, right? Suppose I told you many times, variable selection is one of the most important thing for the modeler. Suppose you are doing a simple regression model, like the multiple regression model, but you have omitted one of the important variable from your model. Maybe knowingly or unknowingly, or by mistake, you omitted the important variables from your model. So for this reason, you might suspect your data might suffer from heteroskedasticity problem. Anyway, a lot of causes also, I told you in the previous class, like when you might suspect the multicollinearity problem, it might also occur or occurs due to the data collection process. When you have faulty data collection, when you have some under specification or misspecification in the model or data set, right? Or incorrect data collection. So here again, the heteroskedasticity might occur, right? So data collection is also important. Without good data, your model is not going to be perfect. Without good data, your assumption or your inference about the estimation of your data is not going to be perfect, definitely. So this might another cause of heteroskedasticity, like the sources or the method of data collection, right? This is also one of the important thing. Anyway, still now we learn what is heteroskedasticity and what is the practical example of heteroskedasticity, right? Then the next slide is like, what do you think? The first graph shows you the homoskedasticity. The second graph shows you heteroskedasticity, but I want to really know, what do you understand from this graph? Like, if I ask you, could you please explain why I term this first graph as the homoskedasticity related graph, and why the second graph is related to the most common problem, like the heteroskedasticity problem? Could you please explain?
So yes, first graph.
Sir, error term is constant, but in the second
graph, the first graph, sir, we see the two graphs are scatter plot, and the first one, if we add a trend line in the first graph, okay, then the values of this observation near also about near this trend line, and if we add a trend line in the second graph, then we can see that the observation are very far from the trend line.
Exactly. Anyway, so that is the another thing. It's a very good answer, I guess, and it was really a great answer. But what I can see, maybe I can try to write a pattern from your like the graph. So if I write a pattern like this, you see, I think it's almost constant, right? You see the pattern is almost constant, but here you see it's very difficult. But maybe I can draw a line from here. It's not constant, you see. It's like here is very small, then it's very difficult, right, to predict. Sometimes here is very small also, right here. So this is a funnel shape, right? Funnel. You remember the funnel shape? You know about the funnel?
Yes, sir.
Okay, so I think you understand. So this is called the heteroskedasticity. So from the graph, you can easily trace, and from the graph, you can easily identify where there is a heteroskedasticity presence in the data set or not, right? So this is the basic thing for a statistician. When you get a data, that the next job of a statistician is to plot the data. And based on the plot, you can find some interesting pattern from the data, right? So yeah, right, for these two figures, definitely you have some data, right? So based on the data, suppose you draw this pattern or you just construct these two plot. So based on these two plot, you can conclude that there is a heteroskedasticity problem or not, right? So this is the basic, what should I say, like this is the basic visualization of your data by which you can understand whether there is a heteroskedasticity problem or not, right? So let's see So what we did, we plot with the random data showing homoskedasticity in the first plot, because at each value of x, the y value of the dot has about the same variance, right? That is the good explanation. But what's about the next graph? I did the same thing. I did plot with the random data showing heteroskedasticity. That means the variance of the y values of the dots increase with the increasing values of x, right? So the later graph, that means the second graphs, you might suspect that there is a heteroskedasticity problem. Good, perfect. Then what's about the reasons of heteroskedasticity? There are many reasons, I told you. There are many reasons why the variance of error may be variable. What do we mean by this sentence? Can you explain? The variances of error may be variable.
Yes, here the value of UI will be changed.
I request you, when you are going to talk, okay, I think some 3 or 4 people intending to talk together, that is not the good thing. Try to give the floor to you, another friend. So I repeat again, what do you mean by this sentence? The variance of error may be variable.
Sir, variable means it may be changed. The error term may be changed by.
Exactly. So this is the non-constant. The sentence, you can change the sentence like the variance of the error is not constant, or the variance of the error may be inconsistent, right? So this is the heteroskedasticity, right? So there are several reasons why heteroskedasticity occurs, some of which are as follows. What are those? Following the error learning model, as people learn, their errors of behavior become smaller over time. Consider one example. For example, the number of typing error. What do you think? First, suppose I give you some assignment. What are the assignment? You have to write some Bengali words or sentences using the Microsoft Word. So, you know, it's really difficult if you have no experience with writing Bangla typing, right? It's really very difficult. But how can you decrease your typing error as the time goes on? The more practice you have, the typing error must be reduced, right? So it depends on your practice of typing. So this is a very classic example, like number of typing error can be reduced with number of efforts you can make, right? As the number of hours you put in typing practice increases, the average number of typing hours as well as their variance decreases, right? So this is a very classic example, like why heteroskedasticity error. So for this kind of example, you see that you can find the large differences, like what I mean in my previous slide. Here the sentence is that there is a large difference among the size of the observations. So these kind of things happen for this kind of classic example, like typing error, right? Or your behavior becomes smaller over time, right? Or maybe your behavior become very larger over time if you have less practice. So this is the one of the thing. And the second example, maybe as income grow, people have more intention, right, for choice about the disposition of their income, right? Like maybe as your income grow, maybe your interest, like for purchasing some commodity or product, it can be changed a lot, right? So this is another example. Improvement of data collecting technique causes the variance become decreases, right? So I told you data collection is the most important thing for a statistician or for forecasting, for estimation, or for predicting, right? So if you have some problem in the data collection, so there might be heteroskedasticity. So you can remove the heteroskedasticity if you can just improve your data collection techniques, then maybe the variance become decreases. Then or the variance is going to be inconsistent as far as the error term is concerned. So in the presence of outlier, heteroskedasticity always arises. Due to the incorrect specification of the regression model, it arises, right? I told you many times, what is the incorrect specification of the regression model? When you are gonna construct a regression model, definitely we have to use variables are there. So you have to correctly specify those variables. That means the dependent variable must be placed in the place of dependent variable. Independent variable must be placed in the place of independent variables, right? And the estimation of the parameter alpha, beta, right? And the other notations maybe you can use, those parameters must be correctly specified. Otherwise, you might suspect the heteroskedasticity problem. So if also arises, it also arises because of the incorrect transformation and incorrect functional form, right? Suppose I told you to transform your data because your data have a lot of problems. Suppose, but I told you to correctly specify, but rather you incorrectly transform or classify your data. So also you can use the incorrect function. So I told you, okay, you can use the linear regression model, but you use the quadratic regression model or polynomial regression model. That is not good fit. Okay. So due to the incorrect transformation or due to the incorrect functional form, okay, this problem can occur. And for skewness of distribution of regression, it definitely occur. You know about the skewness of the distribution. It's like the peak, right? Peak, right Q, left Q, right? So normally for the skewness, if your data shows the skewness, right? Skewness means there is a huge differences among the observations. So then also heteroskedasticity, you might suspect. So how many methods by which you can detect heteroskedasticity? Mainly there are two methods. Number one is the informal method. Informal is nothing that was the graphical method, which we already showed you, like which we already observed. By which method, like using the graphical method, you can detect the heteroskedasticity problem easily. Then the next one is the formal method. So there are many statistical tests or technique by which you can test the heteroskedasticity problem in your data set. These are called the formal methods. So what are the informal methods? The number one, as I told you, this is the graphical method. So this is the number one graphical method. How you can do this? You can just make a plot residual versus predictor. I think you already know the residual. Could you please explain what is residual?
The residual is the
How can you calculate
Residual is the difference between
Yeah, they try to tell difference between what and what?
between estimated and observed model.
Observed value and the estimated value. Yi minus yi hat.
Very good. So suppose I give you some data x and y, so you can easily calculate residual, right?
Yes, sir.
Right? Okay, good. Then what is the predictor for x and y? Predictor.
Sir, y
In
Predictor is the independent variable.
for
X.
sorry,
Exactly. So now, yeah, predictor is the independent variable. Suppose I give you 3 or 4 variables like y is nothing but the income, x is nothing but your education level, x1, and x2 maybe your gender, right? x3 maybe your job status. So if I give you some data with respect to these variables, can you construct or can you calculate the residual from this data set or not?
Yes, sir.
You can.
Yes,
Okay.
sir.
So you already know the predictor as well. What are the predictors are here? I just explained to you right now.
the independent variables.
Predictor. The predictors are the independent. The income is the dependent. Sorry. The predictor will be here. I told maybe what I told.
Expenditure.
the income.
Expenditure.
Education qualification.
Exactly. Okay. So in a nutshell, it's like the independent variables, right? So you can just easily plot. Okay. So after having the plot, how can you conclude that this data have heteroskedasticity problem? Let's see. What is the decision? The decision is that a funnel shape indicates that the heteroskedasticity occurs here. So I think you already know what is the funnel shape. I already told you the funnel shape is like this. Okay. So this is the funnel. Or maybe. Okay. don't focus here. The funnel shape is like this. Okay. Don't focus the round shape. Anyway. So another one is the residual versus fit plot. Can you understand what is residual and what is fit?
Yes, sir.
I think you understand. So how can you conclude that your data suffers from heteroskedasticity problem? Here again, if you can find the funnel shape, it indicates the heteroskedasticity problem. Clear? Is it clear or not?
Yes, sir.
Yes, sir.
Very good. Perfect. The next one is the square residual versus predictor plot. Okay, could you please explain somebody what is meant here, square residual and predictor?
Sir, yi minus y hat whole square are versus independent variables plot.
Yeah, very good. Like whatever you get, the residual, you have to just square the residual. Okay, and the plot will be square residual versus predictor. And if the plot, if the square residual increases for higher value of x, we suspect that the existence of the problem of heteroskedasticity. Can you understand this point? Suppose you have the squared residual. Okay, after suppose I give some data and I ask you to calculate the square residual from the data. Suppose now you have a new column, new data, new variable, square residual, and you have also x variables. Now you can make a plot, normal scatter plot maybe. Then if you can see the squared residual increases for higher values of x. Suppose the value of x is increasing, also the square residual is also increasing, then you might suspect that there is a problem of heteroskedasticity. You clear?
Yes, sir.
Not clear?
Yes, sir.
Suppose this is a plot, this is x, right? And this is the square residual. Okay, suppose square residual, right? So here, suppose you can find the straight line. Like with the increment of x, the error is also increasing, right? So here you can suspect that there is a heteroskedasticity problem. You understand what I mean?
Yes, sir.
Yes.
Perfect. Perfect. So then again, you can also plot the square residual versus fit plot. Okay, how can you conclude that then? The same thing, if the squared residual increase for higher values of x, you can also suspect that there is existence of heteroskedasticity problem in your data set. I think you can easily do this. So the graphics. So now it's your turn to give me the answer. So I show you many graphs are here. Then tell me which figure shows the heteroskedasticity problem.
Sir, figure B.
Sir,
Figure B.
Figure B. What? Start with the figure 1. What problem with the figure 1?
স্যার ফিগার বি তে হচ্ছে আমাদের ভেরিয়েন্সটা হচ্ছে কনস্ট্যান্ট নেই, ওটা হচ্ছে বাড়তে আছে, কিন্তু অন্যগুলাতে একই ভাবে কনস্ট্যান্ট আছে।
Okay, maybe in figure 1. Okay, this is your assignment. Okay, this is your assignment, but definitely in figure B, figure 1, this is homoskedastic or heteroskedastic? Figure 1.
Heteroskedasticity.
Exactly, that means equal variance. But figure 2 definitely heteroskedastic, right? And for the other figures, this is your assignment. What is this one? What is this one? This one. Okay. So try to explore. Yes.
Curvilinear. Yeah.
Yeah. Someone is polynomial, curvilinear, quadratic, right? I understand the pattern, but I told you which figure shows the heteroskedasticity problem. But we are pretty sure that number 2, that means number B figure is definitely, it has heteroskedasticity problem, and first figure have is homoskedastic. That means there is no heteroskedasticity problem, but we are not sure about the other figures. But this is your assignment. Okay, try to explore whether the remaining 3 figures have heteroskedasticity problem or not. Clear? So now it's time for the formal test. So there are many statistical tests you can use for detecting heteroskedasticity problem in your data. What are those problems? What are those tests? Number 1 is the Park test. And number 2 is the Glaser. Number 2 is the Glaser test. Number 3 is the Spearman rank correlation test, Goldfeld quantities test, Bruce-Pagan-Godfrey test, and White's general heteroskedasticity test. So these are the formal tests or formal methods by which you can test or you can detect the heteroskedasticity problem in your data sets, right? So maybe we'll try to have a glimpse of idea or like better explanation when we will do the practical task, right? Then I will try to give you how to perform this test, right? For this class, let's skip it. But then how to remove heteroskedasticity problem, how to remove? So there are many methods. So normal, the common methods, I think I have to tell you, transformation is the best way. So you can transform the dependent variable, maybe, or one way to fix heteroskedasticity is transform the dependent variable in some way, right? So you can transform based on the data types. Also redefine the dependent variable, like suppose maybe mistakenly you choose the wrong dependent variable. Okay, so you have to correct the dependent variable. So you can redefine the dependent variable. So this is another way you can fix the heteroskedasticity problem, right? So finally, this is important. You can use the weighted regression modeling. Weighted, that means WLS. Weighted least square is nothing but the transformation of OLS. What is OLS?
Ordinary least
Ordinary least. Exactly. If you can just transform the OLS to WS, as the name suggests, weighted least square, that means you have to give some weight. Suppose this is the regression model, y is equal to alpha plus beta xi, right, plus error. So you can just give some weight. Weight means maybe you can put something here, you can put something here, right? So this is the transformation. So this is called the OLS. OLS, or weighted least square, is nothing but the transformation of, sorry, WLS, that is weighted least square, is nothing but the transformation or giving some weight, right? How can you transform? You can just give some weight in the variable. So this is the transformation of OLS, that is ordinary least square. So this is a very good technique or regression by which you can remove the heteroskedasticity problem from your data set. So this is the end of our today's lecture on heteroskedasticity. So I